Well, let's look in a little more detail at light, which, as I've said, was electromagnetic radiation, really. And so, really, we'll look at uh, uh, some fundamental work that was done by James Clerk Maxwell in the middle 1800s. And I'll just state them here. But Maxwell developed, at least what's in modern day notation, is what are called Maxwell's equations. It's the divergence of D is equal to the charge density rho. The divergence of B is equal to zero. The curl of E is minus the partial of B with respect to T. And the curl of H is the current density, J, plus partial D with respect to T. And in these, D is just epsilon E, and H is 1 over mu B. D is the displacement, usually called the displacement field. Sometimes it's called the flux density. But it's just this constant, the epsilon times the usual electric field, E. This constant epsilon is the dielectric permittivity of the medium that this field exists in. I'm going to be assuming, and that's really inherent in this, that we're looking at a isotropic, homogeneous medium in all regards. The divergence of the magnetic field vanishes. The curl of E is this one, and then this other one, H. So E and B are electric and magnetic fields, and then H again is usually called the magnetic intensity. Sometimes it's called the magnetic field, and they call B the magnetic induction or the magnetic flux density. I'll generally just call it H. And J is the current density, D, of course, is here. And H is, again, for linear medium, is 1 over mu times the magnetic field. And mu here is the magnetic permeability of the medium. So these, for us, are just constants that characterize the medium that this electric field exists in. So it could be empty space, in which case these become epsilon naught and mu naught, the dielectric permittivity of the vacuum, and the magnetic permeability of the vacuum. Maxwell developed these equations from some general considerations, and then one of the things he showed was that they have a electromagnetic wave solutions. And in particular, if I look at the case where there aren't any free charges, so there's no charge density, there's no currents or current density, so I'm setting both of those equal to zero, then the equations become, in a vacuum or in a homogeneous media, become this set here, and I've gone ahead and substituted in for D and H the two relevant expressions from up here. And then rearrange things since since we're treating epsilon as a constant. It doesn't have to be, but it could vary from point to point in the space. But for right now, let's just look at a nice homogeneous isotropic media with constant epsilon and constant mu. So I can pull that outside and then divide it out. So this equation simply becomes equation 1. This equation, I can pull the mu outside, again it's constant, pull the epsilon outside, multiply through, and get equation 4. So these are the starting point to develop the waves. If I start with equation 3, and that's this one here, and take the curl of both sides, so curl is del cross, I have over here a curl of a curl, and on this side I get the curl of this minus partial B with respect to T. And I can interchange these. Partial derivative with respect to T is independent of these partial derivatives with respect to X, Y, and Z, so I can switch the order and move this operating strictly on this vector. But I can use in this fashion. We'll keep this one the same. Del cross B, I can use equation 4 because if you look, the curl of B is mu epsilon partial with respect to E, the partial with respect to T. And so I replace this by mu epsilon partial E vector with respect to time using equation 4. And then I can use a vector identity. You can look it up, but the curl of a curl turns into the gradient of the divergence of the vector minus the Laplacian operator operating on the vector. And this one, the right-hand side, I can pretty obviously bring these out, and then I have two derivatives with respect to time of the electric field. I get this equation, and then usually you see this multiply through by a minus sign and then bring this over to the other side. That's for the electric field. You can do a similar kind of calculation for the magnetic field. For it, you would take the curl of 4 on both sides and then use 3 to eliminate the curl of E on this side, and then use the fact do the same expansion of the curl of B, and use that the divergence vanishes. And what you find is that the magnetic field, I didn't write it here, I just stated it, but the magnetic field, a similar equation is obtained for it. In other words, if I substitute, put in the B equation, I would get the same equation for the magnetic field. If you look at that, well, that's like a three-dimensional wave equation, provided I identify this epsilon mu here with 1 over the velocity of the wave squared. So if I set v equal to 1 over the square root, then this equation up here can be written as a three-dimensional wave equation with this constant v here being identified with this 1 over the square root of mu times epsilon. If the medium is a vacuum, then I know these fundamental values for the vacuum. And for the vacuum, I can substitute in these two. And when you do that and substitute in the actual values for mu naught and v naught, what you find is you get 2.9979 times 10 to the 8th meters per second, which Maxwell did and identified that as simply the velocity of light. So one can have this expression for the velocity of light in terms of this electromagnetic fundamental constants, mu naught and epsilon naught. And our equation then in the vacuum, it just becomes a c squared here, where now c is 1 over the square root of mu naught epsilon naught. Well, that leads to some interesting implications. I usually use the dielectric constant kappa here for or kappa sub E for the dielectric constant, but nowadays people tend to call that the relative permittivity, and it's just by definition the epsilon of the material to the epsilon of the vacuum. Okay? Or you can, of course, rearrange that. Notice that this relative permittivity is dimensionless. I can do a similar thing for what I would usually call the kappa for the magnetic material, mu over mu naught, but nowadays it's generally called the relative mu sub r, so these are just definitions. The ratio of the magnetic permeability of the material divided by that of a vacuum, and then of course you can rearrange that in these fashions. Again, notice that these relative permittivity and the relative permeability could parameterize the material, but in dimensionless form. Neither one of them have dimensions. Well, I can solve this for epsilon and mu, and then plug that into, for material media, I can plug that into our expression for the wave that we get from the wave equation. And when I do that, I can separate out. I'll have the mu r epsilon r. Those are both dimensionless, and the square root of mu naught epsilon naught. But remember that 1 over the square root of mu naught epsilon naught is just the speed of light, and so I can replace that then with the wave velocity in a medium that's characterized by a relative permeability of mu r and a relative permittivity of epsilon r is just the speed of light divided by that square root of that factor. And again, you may see this written as Ke for the relative permeability, really kappa E, and kappa m for mu m for these relative permeabilities. I'll keep the more modern notation. But remember, from early days of optics, they had defined the index of refraction of a media to be the speed of light in the vacuum divided by the speed of light in the medium. But now we've got the speed of light in the medium given by Maxwell's equations as related to these constants of the material. And so I just substitute this into here for Vm. It becomes C, and Vm is the velocity in the media is just this. The C's go out, the square root flips over on top. And so we find that Maxwell's theory not only predicts plane waves, but that they travel with the speed of light, so it's natural to identify it with light. And moreover, if you do that, it gives you a prediction of relating the index of refraction of the medium to these more fundamental constants, namely the relative permittivity and the relative permittivity and permeability, square rooted. And those were subsequently confirmed. And as a result, Maxwell's equation, because of its prediction that waves, electromagnetic waves, traveled at the speed of light, that it was natural to posit the theory, especially once they found the index of refraction matched up with light in various media, that light was an electromagnetic wave. Now, for us, you often see this approximation. For most transparent media, the relative permeability of the material is close to 1. It's like 0.97 sometimes, or 0.997, things like that. Or it's 1.05 or 1.04, things like that. But in any event, it's close to 1, and when I square root it, that makes it even closer to 1. And so, to a very good approximation for transparent media, the index of refraction is approximately equal, if I set this equal to 1, simply the square root of the relative permittivity of the material, that it's a transparent material that it's propagating, the light's propagating in. Notice the relative permittivity is just epsilon by definition, epsilon of the material over epsilon naught. And if I'm in the vacuum, epsilon naught is E, and so I get epsilon naught over epsilon naught, so the index of refraction of empty space or vacuum is simply 1, as you know that had been concluded earlier. So the Maxwell theory, really, electromagnetic theory, led to the electromagnetic theory of light, and that became well established as time wore on in the late 19th century.